Okay, so in the last lecture, we were talking about the 555 timer being used to debounce a switch, and that typical debounce was around 100 millisecond. It might be lower or higher depending on the type of the switch. Uh, we are using a push button, and we are using that particular symbol to indicate a bouncy switch. Which is connected directly to pin 2, and we ideally want a waveform on pin 2 which looks like this, is high most of the time, meaning when the switch is not pressed, and then when the switch is pressed it goes down and comes back up again very quickly, because you don't press the switch for a long time. You press it and you release it very quickly. Now whenever we do that, if that is the waveform that goes to pin 2, and we manage that by using this pull-up resistor and ground on both sides of the switch. So when it is pressed, it is ground. When it is released, it is going to read high because of the presence of the pull-up resistor. If you are able to do that, then because pin 2 is an input to the trigger comparator, which is comparing one of the points, that one of the references for the trigger comparator, which is inside the 555 timer, is 1/3 VCC. So when the voltage on pin 2 goes below that 1/3 voltage value, what is going to happen is we are going to start charging this capacitor C1. So on another plot, I'm going to say what is going to happen when that happens, when we start, when we go lower than 1/3 VCC. So when you go lower than 1/3 VCC on pin 2, for the capacitor, which is essentially pin 6 and pin 7 voltage, right? This is pin 6, 7 voltage with respect to time. It is going to be low until it hits the 1/3 voltage, and then it's going to start charging up, and that is aligned in time with that point. And it is going to charge up until pin 6 or 7 in this case reaches 2/3 VCC, because inside the 555 timer, pin 6 is connected to the threshold comparator, which has one of its references as 2/3 VCC. So until it reaches 2/3 VCC, it is going to go up and then come back down, because then the capacitor will discharge through pin 7. And we talked about all these details in the previous class. This is just a quick recap. Um, and as this pin 6 and 7 is going up, meaning the capacitor is getting charged, pin 3 is going to output a clean pulse during that time. So if I zoom in on this and look at what time is that going to be, it's going to be from here to here. So that way we get a clean pulse responding to a switch. This might be glitchy, by the way. So it might have some going up and down here, up and down here. It doesn't really matter. Until the voltage on the capacitor reaches 2/3, which is independent of the state of the switch, it is going to keep rising. So it's going to ignore whatever happens at the switch in that time between 0 and 2/3 of the voltage. So that's a quick recap of what we did in the last class. Today we are going to move ahead and talk about the average power consumption, and we are going to build two circuits. So we are going to differentiate two switch debouncers based on 555 timer, and we are going to attempt at more power consumption on an average versus less power consumption on an average, and how we can use PSpice to monitor it. So let's go ahead. In terms of our um, agenda for project 3, we had 5 items in total, and we did the 4 of them, first 4 in the last lecture, and today we are going to be focusing on item number 5, improve the energy consumption. So let's see. We talked about the debouncer switch. So let me talk about the design equations. So the duration of time for which the output stays high. So if the output is giving us a clean pulse, for how much time is it on? Well, that equation is 1.1 times R1 times C1, where R1 and C1 correspond to the design values that we have chosen here and here. And initially we said let's start with R1 being 100K, and then we will choose C1 appropriately such that we get a duration of 100 millisecond for TD. And the reason why we said 100 millisecond for TD was because the design challenge in the project was to was to debounce the switch for more than 100 milliseconds. So that's why we got that number. Let's come back. Let's get into this again. So that's how we got this. And the factor 1.1 comes from the charge equation of the capacitor. So during the charge cycle of the capacitor, the output, which is the voltage across the capacitor, can be expressed in terms of the input voltage and the time constant or decay constant tau. So the output voltage increases exponentially based on that equation. So if we want to find out how long does it take for a capacitor with time constant R1C1 to go from 0 to 2/3 VCC, we can plug in those numbers and find out that that particular value is 1.1. We did this for the 555 timer in the astable mode, and we got that natural log of 2 factor in a very similar fashion. Okay, so if we are okay with that design equation, we can plug in numbers for R1, and then we calculated C1. It came out to be 1 microfarad, and we said, okay, let's use this R1 and C1, build our switch debouncer, test it using a fake switch, test it using a real switch, and then we used a counter, 4-bit counter, to trigger it. And then once we started putting things to a very complex test, it turned out that 1 microfarad capacitor wasn't enough. So we actually had to increase it to 2 microfarad to make sure that the counter doesn't skip any states. So that's what we did the last time. Now we are in differentiating between two different types of circuits for the same debouncer application. So the equation that we are going to work off of, the design equation, is going to be the same. And circuit 1, we have finished it. We have taken R1, we have taken C1, we got that particular time duration for the pulse. That's done. Now what we are going to say is, if I were to choose a different value of R1, let me write R1 here, and if I were to choose a different value of a C1 such that my TD remains the same, does it improve or hurt my average power consumption? So for example, my circuit 2, I'm going to use 10 kilo ohm for my R1, and proportionately I have to increase C1 to maintain TD to be 110 milliseconds. So I'm going to increase this guy to say 10 microfarad. So if I use R1 and C1 to be 10K and 10 microfarad, I should be achieving a 110 millisecond time duration pulse. So that's my circuit number 2. And the only way I can test this, well, let me ask you this. Before I actually put this into a test, I'm going to ask a question and check our understanding. So question is, which circuit 1 or circuit 2, which circuit will consume less average power? Meaning, if you observe it for a certain amount of time, on an average, which circuit will consume less amount of power? And because this has to respond to the pressing of the switch and releasing of the switch, we are going to assume that the pressing of the switch and releasing of the switch is exactly the same for both circuits. Which one is going to consume less power? Well, the key lies in R1. And if you look at R1, over here we have a really big resistor drawing small amount of current from our power supply, and R1, which is 10K, relatively it's smaller, so it's going to draw more amount of current from our DC power supply. So because R1 leads to drawing less current from my power supply, I'm going to answer that circuit 1 will actually consume less average power. So whatever we started off with was already good. But just to make sure, we are going to have to run both of them. Say using PSpice, we can actually check which one consumes less average power. So I'm going to actually do that demonstration for you today so that you can see it on your end. Uh, Before I show you the capture, let me actually start the software so that it's, in the meantime, it gets loaded up. And while that is happening, we can talk about why am I not using waveforms and analog discovery to check which one consumes less power. As you know, in order for me to find out how much current how much power is being supplied by the analog discovery voltage supply, I'm going to have to put a resistor, and we have seen the role of current sensing resistor in previous experiments and projects, and we will see more of that even in experiment 8. Yeah, I'm going to have to use a resistor right out of whenever I have, so for example over here, I'm going to have to place a resistor right after that source, right there. And I'm going to have to measure the current that flows through that resistor. And I can do that using analog discovery by measuring the voltage across the resistor, dividing it by the value of the resistor to find out the current. Once I know the current, then I can use voltage versus and current product of voltage and current to find out the power. So I can do that. The issue is that is going to be very tedious for me to do that. So I'm not going to do that in analog discovery, and instead I'm going to do that in PSpice. So I will show you how to find the average power in capture PSpice. So I have built up my circuit. I'm not going to share the design just so that you have something to do by yourself, because if I share the design, then literally the project is done for you. So I will not share everything about my simulation. However, say when I run it, so I've made my switch debouncer circuit, I've run it, and I will share my uh, results as soon as they pop up. Okay. And as you can see, it is taking quite a bit of time, and there is a reason for that. I chose a very small step size for my simulation just so that I get all the points and I don't miss any data point. So the red one is the pin 3 output that is being shown, and green is the pin 2 input. So green is the bouncy switch, and the red is the clean debounced output. So for example, if I wanted to find out the average power that is being supplied by the voltage source when I use this particular resistor capacitor combination, by the way, in this particular design, I'm using 10 kilo ohm and 10 microfarad. So this is our circuit 2. Um, so if I wanted to find out the average power, then I'm going to have to add a trace. So I right clicked on my plot, and oh come on, and I added a trace, and if I go all the way down, it is going to give me an option which starts with W, standing for wattage. So it's going to say if I wanted to find out the power, instantaneous power, meaning power as a function of time, for V1. I'm choosing V1 because V1 is my DC voltage supply in my circuit. V2, V3, V4, V5, V6 are voltage supplies that are together um, doing the fake bounce switch model. So V1 is my DC supply that I have fixed to 5 volts. So I'm going to select that. I'm going to say OK. So once I get that, as you can see, it is all 0 here, because in relationship with the other two traces, it is pretty small. So what I can do is I can delete the other two guys, and right now I can see the wattage. And again, I can um, change the width of this guy so that it is very clear. So that's the average power being consumed by, sorry, this is the average power, right? This is average power consumed by DC voltage source V1, which is I have set to 5 volts. And as you can see, it is negative. So if I zoom in, let's see, I wanted to zoom here. So if I zoom in over here, you can clearly see that the value is around negative 2.6 millivolts, because this is the power that is being absorbed by the voltage source. It is negative, which essentially means that this is a voltage source and it is actually supplying power and not absorbing power. So to get a better idea about these numbers, what I'm going to do is, instead of looking at positive, I will look at negative. Negative capital W wattage for V1. And the reason why I did that is because I want to look at the power being absorbed, sorry, power being supplied by that voltage source. So the power that is supplied by that voltage source is now showing positive, and the if I took this time scale and I actually found out the average, I will get the average power. However, if I just want to compare two circuits, then I really don't need to do all the precise calculations. What I just need to check is, where are these numbers lying? So all this is around 2.6 milliwatts. All of this during the transition, when you press that switch and when the capacitor is charging, it is starting at about a little bit more than 3 milliwatts and going down to about uh, slightly less than 2 milliwatts. So the average is somewhere around 2 milliwatts there. And then back in the end here, it is back to 2.6 milliwatts. So this gives you a quick idea about what that average is going to be like. It's going to be around 2.5, 2.6 milliwatts. So if I wanted to actually go ahead and compare, I can run this simulation for circuit 1, which is R1 is 100K, C1 is 1 microfarad. So I quickly change the numbers, run the simulation again, look at the average power, and compare the two circuits. One will clearly be better than the other. And as I expected, your expectation is circuit 1 should be less average power. So something less than 2 milliwatts should be a reasonable value to expect. Okay, so that's your two circuits and how to find average power, and um, the design choices that go into improving the energy consumption of a 555 timer based switch debouncer. Okay, so in terms of content, I wanted to discuss that. So let me stop the recording and then we can take questions.